which are available with us for measuring the temperatures. We have discussed that. And then we have looked at the basic classification of different temperature sensing techniques. So based on what principle, based on different principles, we have ordered them, such as liquid in glass thermometer, bimetallic constant volume pressure thermometers, RTDs, thermistors, thermocouples, and then semiconductors. And finally, changes in emitted, based on the principle called as changes in emitted thermal radiation. We also have some more temperature sensing measurement devices, temperature sensing or measurement devices. So we will actually have a look at this particular fourth portion is pending according to me. The other things like starting with uh, ideal gas thermometer, which depends on the physical changes in physical dimensions of variations in the heights of the liquid columns. How do we measure temperatures? So we started with that, the ideal gas thermometer. We have gone through these ideal gas thermometer, and then as a part of temperature measurement by mechanical effects, we also looked at bimetallic thermal strips. Then we also moved on to temperature measurement by thermoelectric effects, where we are directly converting the temperature difference to electric voltage or vice versa, and then measuring the temperature. So that is the working principle in using the thermoelectric effects. In that we have already looked at Seebeck effect, Peltier, and Thomson effects. And then different types of thermocouples. What are the thermocouples? Different thermocouples are made up of. What are the temperature ranges? And what are the advantages of using thermocouples? We have looked at. And then disadvantages while using the thermocouples. We also discussed this quite a bit. And then we have also looked at temperature measurement by thermocouple circuit, how we are actually using the thermocouple circuits to measure the temperature. We have spent a lot of time on this. And then we also looked at the rules which are available for analyzing the thermoelectric circuits, like law of intermediate materials, law of intermediate temperatures. So one of the question is given on law of intermediate temperatures within the exam. And then we also moved on to find out conventional differences using cold junctions. How do we do cold junction compensation? All that we have seen. And then by using a series of thermocouples, how do we estimate the temperature measurement accurately in series and in parallel, which we call it as thermopiles. We discussed about thermopiles, which are connected in series and which are connected in parallel. What are the basic differences between them also we have looked at. And then later we have moved on to a very interesting topic called the resistance temperature detector, RTDs, and thermistors. Both we have spent a sufficient amount of time on both of them. So resistance thermometers, based on our temperature, the resistance gets varied, and by measuring the variation in the resistance, we are able to measure the temperature. So this is basically RTD principle, resistant thermodetectors. And we also looked at the advantages and disadvantages of the RTDs compared to thermocouples we have discussed. And choice of when we take the choice of using RTD or when we want to use thermocouples, at what what are the various scenarios or conditions where we actually prefer one over the other. We have looked into it. Then basic construction of an RTD we have looked at. And after that, the corrections, that the 3-lead arrangement or the 4-lead arrangement to measure to compensate for the temperatures, how we are actually addressing that, we have looked at it. And then finally, we looked at thermistors. I hope thermistors are also completed, correct? Did we completed thermistors or not? Hello? Is my voice audible? Somebody please answer.
Yes, sir, you're audible.
Yeah, thermistors we have completed, isn't it? You don't remember? So it has a negative temperature coefficient of resistor in contrast to the positive coefficient displayed by most metals. Okay, so whatever happens with most generalized conventional metals, it happens in the other way. These are semiconductor devices where it has negative temperature coefficient of resistance. So it follows the exponential variation with respect to temperature. As temperature increases, it varies in the form of in an exponential way. Okay, so we have given an equation for the resistance R equivalent to R naught into e power beta 1 by T, which is absolute temperature minus 1 by T naught, which is the temperature at zero temperature scale, absolute zero temperature scale. So for a metal at 0 degrees centigrade, 0 degrees absolute temperature scale, what is its resistance? That is basically your R naught and T naught. And what is its temperature? It is being measured with the help of resistance within the element. And we know that the material is having a coefficient, negative temperature coefficient of beta. So this experimentally determined constant varies from 3500 to 4600 Kelvin. So for different materials, it will be different. So by keeping this beta over here, if you can measure R, since we know what is the absolute temperature scale or base temperature, and at the base temperature, what is its resistance, this we can get from the material properties. So if we can measure the resistance within the circuit, then obviously we will be able to find out the temperature. This is the principle that we use for thermistors. So it's a very sensitive device, and because you look at this, it has a specific resistance in an exponential way. As your temperature increases, generally the resistance goes on increasing. That is a positive coefficient of resistance. But here, what we can look at is, here you can see here with platinum what is happening. As your temperature increases, your resistance goes on increasing. Whereas with respect to other materials, there are certain materials or metals which tend to show the resistance reduction with the increase in temperature. So such materials we will call them as thermistors. So we will use them for thermistors. So these are a very high sensitivity device because they are very sensitive, because they follow a path of exponential decay. You can see here, it is not a very smooth or a slope of reduction. It has a drastic change in the slope of this. So for a small change in the temperature, you can see there is a huge difference in the resistance. So that's why it is very, very sensitive. And it can be consistently performs with consistency around 0.01 degrees centigrade by having a proper calibration. So what are the advantages of a thermistor? So advantages are, as we have discussed, it is very, very sensitive. That means for a small change in the input, it gives a better output value. Okay, so the output by input, the change in output by input is basically your sensitivity. And you can see that for a very small change, you can see a bigger change in the output. So its resistance changes very rapidly with temperature. Even for 0.1 degrees centigrade, we have a good amount of change in the resistance. So measurement becomes very easy at a very low temperature levels. Small lead error, as the thermistor itself is of high resistance. So basically the lead errors are low. We don't require to have this 3 lead wire compensation or 4 lead wire compensation, as it has having higher resistance. And it is also having low self-heating, as smaller currents are sufficient for excitation. So you don't need to, they don't tend to heat them very highly, because it gets excited for a very small currents, small amounts of currents. So it doesn't require huge currents to excite themselves. So the resistance changes is also low. Therefore, the amount of heating, or whatever we call it, a self-heating value, is lower for this thermistors. So the other very important feature of these thermistors are, these thermistors can be used as temperature compensation for electrical circuits. So to suppose what if you want to find out the temperature effect of the ambient air, at that if we don't want that ambient temperature affecting the measurement, then we use compensation methods, and thermistors are devices which we generally use in compensation of electrical circuit, temperature compensation in electrical circuits. Now let us move on to the limitations of the thermistors. They are very highly they perform very high non-linear behavior. You can see that the variation with respect to temperature is not linear in nature. It is highly non-linear. It is exponential decay that occurs. And at very high temperature, they are subject to be deterioration. So you cannot go for very high temperature measurements. They are for moderate temperatures only, because the resistance variation is exponentially decaying. So you cannot go for very high temperatures, as it may deteriorate the properties of the material itself. So that is what we can call up to thermistors. So these are basically electrochemical effects. So now let us move on to the fourth topic. If you remember the fourth topic, so when we are discussing the various techniques by which we are actually measuring the temperature, you have classified them as based on changes in physical dimensions, which are based on under that classification we have liquid in glass thermometers and bimetallic elements. Both of them are complete. And then changes in gas pressure or vapor pressure, fluid variation, fluid property variation. Based on that, we have constant volume gas thermometers and pressure thermometers. That this topic is also completed in detail. And then we have change in electrical properties because of the temperature variation. If the electrical properties like resistance and expansions, coefficient of expansions are varying, so by suitable measurement of those properties, we were able to measure the temperatures. And such devices like RTDs and thermistors, thermocouples, semiconductor junction sensors, all this comes under this particular classification. And we have spent a lot of time on resistance, RTDs, thermistors, and thermocouples. And coming to the final one, changes in emitted thermal radiation, we have optical pyrometers, and then we have infrared pyrometers, total radiation pyrometers, and thermal and photon sensors. So we are not concentrating on thermal and photon sensors, but we will try to spend most of our time on optical and two-color pyrometers or total radiation pyrometers. So this is one phase that we will complete in today's class. So, but before going to the what we call as the principle based on the principle involving the emitted radiation for measuring the temperatures, we should be knowing a little background about the radiation. So you might have studied in your first year in basic mechanical engineering some of the radiation principles. I believe you might have gone through. So now let us move on to look at what do you mean by thermal radiation? What is it? Thermal radiation is also an electromagnetic radiation emitted by a surface owing to its temperature. Thermal radiation is an electromagnetic phenomenon which happens from a surface due to its temperature. What does that mean? Every body or every object in the universe, if it is above the absolute zero temperature, then they tend to emit radiation because of the energy possessed by the heat element or thermal energy. So the electromagnetic radiation, which is due to the temperature of the body, which is emitted due to the temperature of the body, is what we call it as thermal radiation. So in this particular class, what we are trying to understand is how do you measure temperature by using radiation principles. So since we are dealing with radiation principles, we should be understanding a little bit of radiation principles that comes in the transfer that may come in the next semester. We will be able to study this radiation principles. So I hope you have studied it, right? Your 3-1 or 3-2? So probably in 3.2 you will be reading you're studying heat transfer course. In that you will have a detailed look about radiation. Here, what I will try to make you understand is I will try to explain the very fundamental principles involved in the radiation. Okay, so there are many electromagnetic radiation depending on their frequencies, like radio waves, X-rays, and all of that, which are being emitted because of various properties of the material. But thermal radiation is solely the electromagnetic radiation due to the temperature of the body, or thermal energy of the body. So every object inside the universe which is having some temperature which is above zero, absolute zero temperature, it will emit some thermal radiation, okay, which is visible to our naked eye within the wavelength range of 0.1 to 100 micrometers. After that, it may not be not visible. Beyond this range, our naked eye may not be able to look at this particular electromagnetic radiation. So we are trying to utilize this principle for measuring the temperature. So that is the soul or net impact of this particular class. So the total emitted radiation. So what here we are giving an expression, capital EB is equivalent to sigma into T power 4. Okay, so this is the emissive power is equivalent to sigma, which is a constant, which we call it as Stefan-Boltzmann constant, and T is the absolute temperature of the body. Absolute temperature scale means Kelvin scale. So based on the absolute temperature scale, we are able to measure this law is called as Stefan-Boltzmann law. So it tells you the total emissive power. What do you mean by emissive power? So in general, if it is conduction or radiation, it is the heat transfer per unit area per unit temperature difference. That is what we are calling it as heat transfer per heat transfer. Okay, Q. If it's per second, then we call it as heat transfer rate. Okay, so if I have just a moment. If I have a body which is particular temperature capital T equivalent to some 400 Kelvin, for example. Okay, so it always, because of its temperature, it always emits some radiation. So there is always some radiation that is being emitted from. So the maximum emissive power, that is the emitted energy, the total emitted energy outside the body, its temperature. Okay, it is basically called the emissive power. This is what we call it as emissive power. So this emissive power of a particular body is basically calculated with the help of this particular equation, where T is the temperature, absolute temperature, that is 400 power 4, and sigma is a constant value, 5.67 into 10 power minus 8 watt per meter square Kelvin power. To use this, we call the standard or the total thermal radiation emitted by a black body. So here, what do you mean by a black body? A perfect emitter is what we call it as a black body. So it can absorb the whole radiation upon it, and it emits perfectly. So whatever that falls upon it, it is able to emit completely. So that we call it as a black body. So here the maximum radiation of a surface of a body, suppose there are two bodies, one is normal body, another one is painted with a lamp black, for example. So this one is coated with lamp black. This is one powder. So when we have lamp black powder coated on top of it, it becomes a black body. And even though they both are at the same temperature, 400 and 400 Kelvin, this this lamp black coated thing, which we are assuming to be a black body, will emit the highest radiation from the surface. Okay, this emits the highest radiation from the surface. So the black body, whatever we are assuming, is a ideal body which we are assuming. Okay, this is an ideal body which we use to measure or to compare any surface with that, to understand what is the difference in the density. So just like heat transfer rate in case of conduction and convection, we are utilizing the radiation principles. Okay, and the radiation principles, how do we so we have a very small wavelength range which can be visualized or seen by our naked eye. So depending on its temperature, the radiation emitted by the body matches that frequency, then our eye may be able to see that color. And if we can manage to observe at what temperature that color comes for a particular wavelength, then we will be able to measure the temperature. That is the problem. Moving on, you will be clear. It will be made clear. So, as I told you, depending on the wavelength, the emissive power is varying. Okay? The emissive power is watt per meter square Kelvin power 4. So, this much amount of energy per unit area per unit temperature it is what we will get. So that is basically Stephen Boltzmann. So watt per meter square per unit area, if this is the surface per unit area 1 by 1, how much amount of energy is radiated? That is my emissive power. Okay, this 1 by 1 area, meter square or mm square, how much is the energy is being emitted? That is my emissive power. So for different wavelengths, as I discussed, so each body in this direction, the wavelength is different from this direction. So we have a different frequency of or a spectrum of frequencies we can observe. It is not a constant spectrum. The frequency is not the same throughout the body. It varies differently. When it comes, the spectrum is different, this spectrum is different. So the wavelength values will be varying. So what happens here is the emissive power of a black body varies with the wavelength. So what is the wavelength that is with which the body is emitting the radiation? Depending on that, my emissive power varies. Okay, so here it may not be the same. The wavelength has a lot of variation. So the emissive power that is coming out is directly dependent on the wavelength, and that expression is given by this particular equation, where the monochromatic wavelength emissive power is basically C1, which is a constant. This is the C1 value. Lambda, that is the wavelength, power minus 5, divided by e power C2 is another constant by lambda. Lambda is the wavelength by T, which is the absolute temperature, minus of 1. So the emissive power depends on what? This is a Planck's equation, Max Planck's equation. So this is dependent on what? It depends on the wavelength of the emitted radiation. If your temperature is higher, your wavelength will be lower. Will reach we will get maximum emissive power at shorter wavelengths. So you can see that from the next equation. So C2 is this. So those are the two constants. So I will show you the graph related to this. So when thermal radiation, any thermal radiation, that is due to the temperature, there is some emissive power. This is because of its own temperature. It emits some radiation. Apart from that, when some thermal radiation strikes a surface, so this is the body, because of its temperature, it is able to radiate some heat energy. Apart from that, similarly, there is another body which is also having some certain temperature. So it is also radiating some energy, right? So this incident radiation will undergo three processes. One is it may be absorbed in the whole body, which is denoted by alpha. It may be reflected back. The same energy may be reflected back. It is your rho. And the third one is it may be transmitted. The sorry. The energy that falls onto it may pass through the structure and leave the structure from the other side. So this is what we call it as transmittivity. Most of the metals, transmittivity is 0. Okay, for most of the solids, tau is equivalent to 0. Therefore, so alpha plus rho is equivalent to. So there are two radiations which we are looking at. One is because of the induced temperature, because of the internal temperature, emits radiation. Number two, because of the incident radiation, some part may be absorbed, some part may be transmitted, but some part may be again reflected. Therefore, we are defining a new term called as emissivity. Okay, so what do you mean by emissivity? Emissivity is equivalent to the emissive power of a body to the emissive power of the black body. So it is like a scale. We know that the maximum emissive power for a particular temperature will be given away by the black body, and whatever the body that we are having at our hand, how much at the same temperature it is able to emit. So the ratio of these two will give us a new parameter called as emissivity. So under equilibrium conditions, under thermal equilibrium conditions, what we can assume is your emissivity should be equivalent to your absorptivity. Okay, again, emissivity is a different thing. So it is not a constant value. It varies, or it is a function of surface finish. It is a function of color. It is a function of oxidation that is happening on the surface, and it is also dependent on the age. So depending on all these factors, your epsilon or emissivity value will vary. Therefore, it is prone to more uncertainty in the measurement of temperature. So you can see over here the emissive power, the monochromatic emissive power, you can see over here. Okay, with respect to wavelength. So this is 1 micrometer, 2 micrometer, 3 micrometer, 4 micrometer, so on and so forth. Here, for at a particular temperature, T is equivalent to 922 Kelvin. You can see here, as the temperature, for a particular temperature, the black body is having the highest emissive power at a lower wavelength. See? So almost 1.9 micrometers, we are having the maximum emissive power at a temperature of 3000 Fahrenheit or 1922 Kelvin. It is giving at 1.9 micrometers, we are having maximum emissive, beyond which my emissive power is reduced. Similar thing that you can also observe here, that for a gray body means any body which is not black body generally tend to have it as a gray body, because it only emits a part of the black body. It will not be exactly equal to the total emission emitted by a black body. It is lesser than that. So any surface which is not a black body, we generally tend to call it as a gray body. So you can see here, it may be 0.6 for the gray body. Okay, so gray body is also an ideal case of it. But when it comes to real surface, you can see that there is a lot of variation in the emissive power with respect to the wavelength. It's not a smooth curve. Okay, we have a lot of variations. So what we do is, when we want to calculate, we convert the actual surface graph into an equivalent gray body graph, and that value we will take for measuring the total emissive power. Okay, so the emissivity of a gray body is constant for all wavelengths. You can see here, emissive power is same for all wavelengths. Okay, so The next one is we are also having a Wien's displacement law. So this law will show you the emissive power or power density with respect to wavelength at different temperatures. As your temperatures of the body goes on increasing, you can see here this is 3000 Kelvin, this is 4000 Kelvin, this is 5000 Kelvin, and this is 483 or this is nanometer. So it is around 6000 Kelvin. This one is. So you can see here the maximum value we have got for a wavelength of 483 nanometer. Okay, so for 6000 degrees centigrade, 6000 degree Kelvin, for at that particular temperature, you can see that the wavelength of the radiation gives a maximum peak or maximum emission is coming out of the radiation which are at very low wavelength. So you can see here it shifts towards the left. It shifts towards the left. You can see that 483 nanometers is what we can see. The shift in this maximum point explains the change in colors as the body is heated up. So when you are going on increasing your temperatures, okay, when you are going on increasing your temperature, the body temperature starts with red color and converts to orange, and finally it becomes white, comes to white color. Okay, but as your temperatures are increasing, you can see here the colors are being varied. The colors are being varied because it is moving towards the left chunk. So your wavelengths are getting reduced to lower. So here you can see that it gives maximum power density or emissive power at 483 nanometers. When it is at 5000 Kelvin, the same material at 5000 Kelvin, you can see here the maximum value is available at 580 nanometers. Okay, so that is the total maximum emissive power we get at a range of 580 nanometers. Similarly, at 4000 we have 724. Likewise, you can see here at 3000 Kelvin it is 966 nanometers. So as your temperature is increasing, maximum emissive power, okay, you are getting at your emissive power density you are getting at lower frequencies. Getting at lower frequencies. See here. Okay, so the same principle we will use. That means when the temperature, for a particular temperature, the body will emit a particular color. So that is mostly clear by this particular. So there are two ways of measuring the temperature using the radiation principles. One is the optical pyrometer. Okay, one thing is the optical pyrometer. The second one is basically finding the heat flux that is falling upon the surface. So here it's a very interesting device that we have. You can see over here we have an eyepiece. So you have an eyepiece. What is the requirement of using a fundamental temperature measurement device which depends on the principle of emissivity? What is the reason? The reason being the temperatures are very high in degree or high in nature. You cannot put an inclusive or touching or materials to the high temperatures. You will not be able to go very near to that. It will harm you. So such temperatures you will not be able to measure. Therefore, what you are trying to do is you are trying to estimate it by means of the principles involved in radiation. Okay, so that is what we are trying to do. So we have a temperature source here which is at very high temperature. Let us say this is at 5000 Kelvin. Okay, so because of its temperature, it tends to emit particular radiation, particular wave, electromagnetic wave radiation, which we call it as thermal radiation. And it comes, and we have an eyepiece over here. Through the eyepiece we can see, and we also have a red filter. This helps in reducing the range of the light. Okay, so the light, if it is very high brightness is required, then you may have to use high powered one. So by using a red filter, you are trying to reduce the the intensities of the light that comes in. The absorption screen also does the same thing. It absorbs the maximum energy, and therefore you will not be required to use very high powers to match with the radiation that is coming out. So we have an optical system and a detector. We have two things. We have a red filter and an absorption screen. Okay. So we know that the output signal of the detector temperature T is related to the thermal radiation of the object with the help of Stephen Boltzmann. EB is equivalent to sigma T power 4. So temperature is, if we want to know this, if you can find out the EB, that is the total emissive power, if you can find out this, sigma is a constant. So if you were able to find out this, you are able, this is a constant, so definitely we can find out the temperature of the surface. This is the principle that we are depending on. So for any surface, we have another term called epsilon. Epsilon is equivalent to E by, that is the emissive power by EB. So for a black body, epsilon becomes 1. That means your emissive power is nothing but the emissive power of a black. For all other real surfaces or gray surfaces, that epsilon value is less than 1 in general. So E is always less than emissive power of the body is always less than emissive power of the black body. Okay, so we have to know the emissivity, we have to know the temperature. In order to estimate the temperature of the body, we have to find out the emissive power of the body. So for that, what we are trying to do is, we have an internal circuit here, the battery, there is a rheostat, and there is a reference temperature lamp in which we have this filament. Okay, we have a multimeter over here. We have an outer tube covering, red filter, and an absorption screen, along with an objective lens. So what happens is, the temperature source will emit radiation, and this radiation will come through the objective lens and focuses onto the filament of the bulb that we have kept as a reference temperature lamp. So we are supplying an electrical energy to the battery, and we are controlling the energy or resistance of the bulb by means of a rheostat. We are also measuring the by a suitable multimeter. We are trying to find out what is the current and voltage that is passing in the circuit, in this particular circuit. Now, this based on its temperature, based on this temperature source temperature, it will emit certain color, which is starting with red to white. It will be able to show that in a different color. So if the brightness, if the background brightness, when you look at through an eyepiece, and the filament based on the temperature, based on the from the battery, it receives current, and therefore it also receives certain temperature, and therefore it emits some radiation in related to the temperature. So the radiation that is coming out of this filament is based on the amount of current which is passing through it because of the temperature. Because of the current passage, it will have temperature generation. So based on the temperature generation, based on its radiation principles, it will emit some color. So we are showing three things over here. The first condition is filament is dark. So filament is shown in a dark color, that is cooler than the temperature source. So the source temperature, that means the source temperature is at a very high temperature, and this filament is shown very clearly, that is very dark in color. That means the temperature of the filament is much lower than the temperature source. Okay, there is another condition, filament is bright. So in here the background is duller, but the filament is bright. So that means it is much hotter than the actual temperature source. So the amount of current that we are sending through the reference temperature lamp is much higher, and therefore it is showing much brighter. It's seen much brighter compared to the temperature source. So that is also not the equivalence of temperature. And we are also looking at the third option, where we will not be able to see the filament at all because it is mixed with the background. So whatever the background color that comes in from due to the temperature source, the color of the filament also matches with it. That means the filament will be burning with that particular amount of color, same color. Therefore, you will not see any filament over here. So what does that mean? the filament of the bulb is acquiring the same color as the temperature source. That means the temperature of the filament as well as the temperature source, they both become equal. So when we know that the temperature source become equal, we will measure using a multimeter what is the Q, that what is the heat energy or what is the electric energy that we have supplied to the heater. So by proper calibration, that means we have the voltage versus current P versus voltage into current is equivalent versus temperature. So V and I you will be finding out from the multimeter. So for different power rating, we have different temperature. So depending on what power you are supplying, when this filament disappears, when it disappears, depending on what voltage and what current, at what voltage and what current it is getting disappeared, that corresponding temperature is nothing but the source temperature. Okay, so if the brightness of the filament is lower than the background, then you have to increase the power. You have to increase the battery input. So once the filament becomes darker, you have to reduce the battery input. And in between these two, there is certain value where the filament disappears. That means the filament acquires the same temperature that of the temperature source. So by knowing the current and voltage reading at that temperature, so we have this we've already prepared the calibration curve with the help of the temperature versus temperature measurement with the filament. So that means you put a thermocouple on the filament, and for different voltage into current, it will have different color. So you'll be able to measure the for particular voltage into current, we have a temperature of the source. So now when it disappears, you'll be pretty sure that it is able to measure the temperature of the source. So that is how we use the optical pyrometers. So we can see that it is a device that from a distance determines the temperature of the surface from the spectrum of the thermal radiation it affects. The same thing I have explained over here. So from this, you know the emissive power, you will be able to find out the emissive power from the battery input. Epsilon is the property which is dependent on many factors, so it has to be very carefully calculated. Sigma is a constant, temperature is what we need to find out. So temperature is equivalent to the capital E by epsilon into sigma, total emissive power by emissivity into your Stephen Boltzmann constant whole to the power of 1 by 4. So this is about optical pyrometers. We also have methods where we try to find out the capital E, the total emissive power, and from that we try to find out the temperature. There is also other way, but here what we are estimating capital E by means of this multimeter, and from that we will be able to find out the temperature of the filament, temperature of the source. Any doubts up to this you can raise now. I hope you understood this concept. Okay, so moving on, the final topic of this temperature measurement, we have unsteady state temperature measurement, where temperature sensor, we have already seen this in the second unit itself, where temperature sensor we are using as a first order system. Okay, suddenly if a step input is given to a first order system, how the output will behave? How the output will behave? Depending on the damping coefficient, or it will slowly go and exponentially matches with the output, but it takes certain time, correct? So here what we are trying to do is we are taking temperature sensor as a first order system. So we have taken a temperature probe as a system subject to transient temperature unsteady. So within the first few minutes, how the sensor is behaving. For that, we have taken a small bead with the thermocouple kind of this thing. So rho is the density of the probe material, V is the volume of the probe material, A is the surface area of the probe, and C is the specific heat, and H is the heat transfer coefficient between probe and the fluid. So here what we are trying to do is we are using the energy conservation. So what does this energy conservation law will say is rate of change of energy stored in the probe, whatever the energy that is stored is nothing but with the rate of heat transfer, how much that is coming in and how much heat transfer that is going out is nothing but the energy stored within this probe, correct? Suppose if I have taken a bath here, there is an input and there is an output. Whatever that is coming in, Q in minus what is that is going out, Q out, is nothing but your Q that is saved or that is stored, Q stored. Q in minus Q out is nothing but Q stored. Similarly, rate of heat transfer between the probe and the fluid is nothing but rate of change of energy stored in the probe. So therefore, from the temperature sensor as a first order system, you know Q, you have seen the convection equation Q is equivalent to HA T minus T infinity, which is also equivalent to minus rho Vc dt by dt. This is the unstudied term. This is the unstudied term. This is the heat transfer rate that is happening between the Q net heat transfer is equivalent to whatever the heat that is coming in and is going out, which is nothing but HA delta T. First year Newton's law of cooling you have studied. Similarly, whatever the heat that is coming in and whatever is going out is nothing but heat stored. So heat energy stored is a with respect to time, it's a temporal quantity. Therefore, it can be multiplied as rho mass by volume into specific heat. Specific heat is per unit volume how much amount of heat is required to raise its temperature by 1 degree. So for 1 degree how much time it is taken. So for this many degrees how much time it is taken. So that will be smoothly giving you the non-transient. So therefore if you are writing this expression dt by dt is equivalent or this plus HA by rho V T minus is there, so this I have brought this side is equivalent to minus 1 by rho Vc HA minus HA by rho Vc T infinity. So this rho Vc by HA is generally what we call it as the time constant tau for the first order system. So this becomes this whole term, if I am writing as tau, then it will become dt by dt is equal plus t by tau is equal to t infinity by tau. So that expression, if you make it simplified, this will be nothing but t minus t infinity is equivalent to e power that expression will come. So equation 4 can be written as dt by dt, that is the temperature or the transient term with respect to of the temperature. T is the time constant and T infinity is the ambient air temperature. So this is the expression for transient measurement of the temperature. So I have given you a very small example. So this I will share with you. Please have a look at it. And this is all about your temperature measurement. So we have looked at different materials or setups or systems by which we measure the temperature so far. So tomorrow's class we will start with flow measurement. Okay. So any doubts on this we will discuss. No questions at all? Okay. If you have no questions, then I will try to stop this class. Any questions? So we will meet tomorrow at 10 o'clock. So we will discuss from tomorrow onwards, we will start with flow measurement. Okay. 1 or 2 classes I have to cover up. So that's why I'm a little bit faster in explaining the things. So even if you have any doubts to be discussed, you can always start that at tomorrow's initial period of time. So when I start the class tomorrow, you can ask or discuss any questions related to today's class. Okay. So if you have no doubts, then I will try to wind up the session. So we will meet. Is that fine? or any questions?
Yes, sir. Fine.
Okay. Okay, guys. Take care. Let's close this session for today.